also on carbonaceous material. Here it's on graphite nanoparticles. Thank you for the introduction. Very happy to be here. So I should have uploaded that earlier, but I'm on now. Thank you. So yeah, I'll start my talk with the beginning of our story, where we started seeing these particles in our premixed flames. And these are higher temperature, meaning about 2200 Kelvin, so hotter than typical flame temperature, laboratory flames and engines. And what we saw were these basically crystals, these graphite crystals. And of course, we were very excited. And we started these experiments by rapidly inserting a TEM grid into the flame. And we saw these particles. Here's an example of just a very crystalline with these nice electron dispersion pattern. And we even got some interesting shapes. This looks like a pyramid here. And we're very excited. And after some thinking, we're pretty sure that these are artifacts from sampling insertion into the flame. And so we also prepared these TEM grids through aerosol dilution. We pull a aerosol sample from the flame after dilution and then deposit on a grid downstream. And so it's still exciting. We do see that there is some amorphous components, but there is definitely some, you could even call it graphenic, more than graphitic, graphene, like some few layers of graphene in the flame. And we also collect these particles by growing a film on a surface, and by collecting this film and preparing a TEM sample from that, we see, again, these looks like more like a multi-layer graphite little particle here, almost like a bean shape there. So that's this talk. I'll look into answering the question is, are these actually formed in their flames, or like these artifacts? What is the competition between the actual flame processes and our sampling methods for preparing this and analyzing these particles? So the flames that we're using here, they're called premixed stretch stabilized flames, which allow you to access these higher temperatures than normal flames. And we have some TEM, Raman spectroscopy, X-ray photoelectron spectroscopy, and particle size by sampling the aerosol. And our main objective is to look at what is actually being formed in the flame, and how does that different from the films that we're making and any artifacts that are possible as well. So the flame, it's unique in that it's stabilized not by any heat loss mechanisms or anchoring mechanisms. It's this steady flat disk floating there by an aerodynamic balance. So because of that balance, you can basically operate at the adiabatic flame temperature or even higher or lower depending on the transport effects. And so it's a relatively simple flow field where you can use this flame and you can understand these very relatively simple temperature fields, just like other pre-mixed laminar flames. You can get these velocity fields and also get a good feel of the growth time and things like that. And this specific flames, it needs this stagnation surface for the stabilization mechanism. And we've embedded a probe in this plate to give you a probe location with better defined boundary conditions so that you can compare to the computations and things like that. In our previous work, we showed that indeed these flames are hotter than usual laboratory flames and engines. And we're still working on improving this temperature method because you can't put a thermocouple in these flames. That will just cause a lot of heat loss, which will not give you the true flame temperature. And so we did this optical pyrometry method by analyzing the soot emission, the radiation from the soot. And an assumption commonly employed in this black body based formulation is that you can assume this optical dispersion coefficient of 1. And when we apply that assumption, we get a very much higher temperature than is probably there. So approaching 3000 Kelvin. So our measurement is still not totally defined, but what we did was compare this to our gas phase computation. And by fitting this optical dispersion coefficient to our computation, it shows that within physical reasonability that our temperature makes sense. It's not a perfect independent temperature measurement, but my point here is that we indeed have hotter flames than normal, but much greater than 2000 Kelvin. And our hypothesis is that if you do have a soot forming flame, then at these high temperatures, you would expect that you would get a unique structure different than soot. And the carbon community has been looking at this forever, and as we've been speaking about today as well. And I've been learning a lot from the carbon community through these studies. And a classic picture is here, where of course, if you're annealing or doing some thermal treatment, you would expect that high enough temperature to get much ordered structures than you started off with. So the experiments today are two different laminar flames, one at 2.6 equivalence ratio, one at 2.77. And based on our computations, we can say that these flames are higher than 2200 Kelvin. And what's unique about these, what's already known about premixed flames and unique about this regime that we've been looking at is that if we have a high flame temperature like this, to have a soot formation at these temperatures, you need to have a much higher equivalence ratio than normal. So another unique thing about these flames in the sooting condition is that you need to have a lot of excess fuel in order for the soot to see soot formation. And that's what causes some unique things that I think haven't been observed before that we'll talk about now. So once we have this soot formation, we'll look at these different characterization and of the materials that we're making. So one way that we sampled these particles was to pull an aerosol sample from the center line of the flame, and then after dilution, analyze the aerosol either by a particle mobility sizer or deposit this diluted aerosol onto a TEM grid. We also used this stagnation surface as a deposition surface to grow these films. So for the particular flames of today, here's one at the lighter sooting condition and a heavier sooting condition. And then you can analyze these films directly. For example, our Raman measurement was on these films. And then you can also make a TEM grid from this powder. And then another common TEM preparation method for flames is to just simply insert quickly a TEM grid to thermophoretically deposit a sample. So to begin, let's look at the Raman spectra that we got from these films here. So we extracted these particles in these three different ways. Here is the film, Raman spectroscopy on the film, and we also looked at the spectra of off-the-shelf hard carbon. This isn't the exact one, but this is the first Google image that popped up. So this is a store-bought powder. And just from the primary peaks on the Raman spectra, we see that our film looks different than hard carbon. And some of you may be familiar with the Raman spectra of soot. This looks closer to the Raman spectra of soot. Ours looks like, you may be familiar with graphite and graphene materials. This looks closer to either disordered graphite or defective graphene. That's the features that we're seeing in our films. And in the secondary peaks, similar to these other graphenic carbon materials. So the hard carbon looks closer to the soot, and soot itself doesn't really have any prominent defined secondary peaks. Our material does. So that's one indication that this high temperature premixed flames does indeed form particles, at least in this film, that it's different from soot, more ordered as we were expecting. And again, we measured this Raman spectra for two different wavelengths, and based on this dispersion in the signal, it behaves similar to these graphene materials. So from looking at the film, we have these properties that are closer to graphene and graphite than soot. This XPS method has been commonly used for carbon materials to determine this contributions of the sp2 bonding versus sp3 bonding. And here is our analysis for these two films here. and then also the hard carbon again. And by analyzing the areas, deconvoluting our signal to these different types of bonds, based on this analysis, the higher equivalence ratio condition has 75% SB2 based on this method, followed by the lower equivalence ratio, and then hard carbon has the least SB2 contributions based on this method. Okay, so looking at the TEM images, here is this two cases of the 2.6 equivalence ratio and 2.77 equivalence ratio. What a lot of these, we took a lot of these TEM images, and first thing we were able to confirm that these are not agglomerates being formed. This is a premix flame with a very short growth time in the flame, so we're not expecting them to aggregate and form these larger fractal particles. We're expecting primary particles at the earliest growth stages, and that's what these TEM images confirm to some extent. And then sampling from the dilution probe to get a particle size distribution based on mobility diameter, we see that these particles are very small, 6 nanometers in the first case and 12 nanometers in the second case. So here we're forming primary particles at the very smallest nanometer scale. So then looking at other regions of this aerosol sample, we can look at, of course, it's hard to prevent them from agglomerating to some extent. And what was interesting in this aerosol sampling method was that we saw these blobs, these amorphous-like sections in this lower equivalence ratio case. And moving closer to this, it looks like some very amorphous carbon structure. But embedded within both of these cases, and more prominent in this 2.77 case, we have these long graphene-like or like multi-layer graphite-like structures where it has the spacing typical to graphene and graphite, and much longer lengths than you would see in soot particles. Soot is more tortuous, and people measure this length of this graphite layers in the long distance, and this is much longer than any reported for soot. And so this is what we're looking at by this aerosol deposition, that for the most part, it's hard to find these features in the lower equivalence ratio, but if the equivalence ratio is increased, you start to see these components. It's amorphous, but you also see these other more ordered structures come out. So here's a couple of more examples. So in 2.6, you can see these a little bit of traces of this graphene-like behavior, but 2.77 cases, it's much more prominent. And then here's another picture where just at first glance, it does not look like soot particles that's depositing on here. You have these much different look to it. So again, what we found was that the question would be what's forming in the flame and what is a product of also the sampling and deposition method that we're using. So here, moving on from using a dilution aerosol probe to prepare a TEM grid, here we took the film that we also can collect and then scraped it off, dispersed it, and drop cast it onto a TEM grid. And what we see there is something different, where it's harder for us to find this amorphous section of this that we saw previously. What comes out more, even in this 2.6, is these long ordered regions of the sample. So here's this 10 nanometer. This is a 10 nanometers here, and this contrast enhanced and things like that. You can see clearly that this is not a soot particle. And same thing with the 2.77 film. So this is typical to what's reported in graphene literature. So instead of graphenic, it's more like graphenic for this film that's broken up and dispersed. So moving forward, when we do a rapid insertion measurement, how much time do we have? 1 minute, okay. Rapid dispersion measurement, rapid insertion instrument does show some soot-like properties, but what's interesting in this rapid insertion measurement, we see that because we think it's because of this high concentration of precursors that's needed to form these particles to begin with, you get some conditions where it can be some artificial crystallization, giving rise to these crystals like this. So in summary, these premixed stretch stabilized flames have this unique condition of higher flame temperatures and very high excess fuel. And we have a mixture of graphene-like behavior and amorphous behavior depending on the sampling method. So where this deposited film looks more like graphene, and we're currently developing new experiments to quantify this better and possibly optimize this artificial crystallization behavior that we're seeing. Thank you for your attention. I'll answer any questions.
Thanks a lot. There's one question.
Congratulations on this very nice and meticulous work. My question is related to how well do you know that the temperature of the soup particles represents the temperature of the gas phase in a flame? I mean, obviously, the temperature experienced by the particles themselves is what impacts their properties, but there are examples in the past work where, for example, people looked at silicon particles formed in cold plasmas, where the temperatures were about 400 to 500, while crystalline particles were formed, which will require temperatures of 800, 900. And they concluded that the particles are actually hotter than the gas phase flames. There was also materials presenting from our work where we looked at the temperature of particles and the temperature of gas phase directly and saw that the particles in some circumstances can be hotter than the flame. What are the chances that this is also the case in your flame? Have you tried to measure the gas phase temperature independently, like with OH, LIF, or NOLIF, or so on?
No, that would be nice to have this variety of optical methods, because you do need an optical non-intrusive method. But it's also possible that the substrate itself, the deposition, like the outside of the flame, we think a lot of the most interesting things is happening outside of the flame on collecting the sample. So that's another temperature. What is the deposition surface? Maybe the gas and all those temperatures involved with the deposition may also have an effect. Yes. Oh, not with time in the lab, but time in the deposition. Yes. No, we look at this. Took us several months to try to play with. Yeah.
We have online questions.
Hi, okay, nice work. I just have a very quick questions. So I just noticed some graphene structures in the middle of the particles, or is not on the surface. I just curious, is that correct? Or based on this, what's the difference about the if the equivalent ratio to 2.6 and 2.7, whether it's just the temperature effect, or there's no temperature difference between these two flames, and the effect that the crystal formed in once the particle already formed, then the crystal structure formed with after the temperature profile in the flames. I mean the temperature effect.
I think that there is temperature effects in the flame and outside of the flame during deposition that can be important. One thing that can be important in the flame would be if you have a lot of precursors and then it undergoes a certain cooling rate at this deposition surface, that can induce some crystallization due to the cooling of low vapor pressure materials and things like that. And then outside of the flame as well, you can have depending on the deposition temperature, this gas multi-component flow coming into the deposition surface. There's a lot that we're looking into right now to try to isolate these competing processes.
All right, thank you.
Next, Carolus.
Hello, thank you for the presentation. I'm just wondering if you have studied any parameters that could affect the size of the graphene that you have at the end, or the graphenic particles, in terms of the lateral size. Like, what could make them be bigger?
The lattice size, I would expect temperature would be the easiest one, that the most direct effect. The higher the temperature, probably the more longer these features would be. That would probably be the first one.
Thank you.
And the last one is Rob Trento.
Hi, that was a very nice presentation. I was just thinking about the temperature, and I think your flame would be a great candidate to use the Krypton X-ray fluorescence spectroscopy method for measuring temperature. Amongst other things, we should be able to resolve whether there's a kind of like a temperature dip inside the flame due to your sampling probe. If you'd like to talk about that at some point, I'll be happy to do so.
Great, yes.
Okay, thank you once more.
I'm sorry, but we have to postpone all other questions to the poster session. We will continue with the next topic. It's also on graphene, and contribution comes from. Oops.